So in this pulley problem, it's a pulley problem that consists of two different chords. One chord is in yellow and one chord is in this light blue. And the problem gives us some more information that an elevator starts from rest and moves upward with a constant acceleration. If W, which is this counterweight, moves through 30 feet in 5 seconds, we're asked to determine the acceleration of the elevator, which is E, and the cable, which is this point C right here. And we're also asked to determine the velocity of the elevator after 5 seconds. So, since it's a pulley problem, the first thing we really want to do is we want to establish our reference datum. And a good place to choose this, well, in this problem really the only place, is through this pulley up here. And as luck will have it, both of these pulleys are in line with each other. And what I like to do is draw a dotted line at every point that I know I need to reference, just to remind me that I need to reference this point. So we have the counterweight, we have E, which is the elevator, and we have this point C. And because we're interested at this point C, we can sort of get rid of this motor right here and just look at point C by itself. Now, since we're referencing from this top datum line, positive is down, and we're going to call this first line SW. I'm going to call this second line right here S of E. And I'm going to call this third line, which is point C, S sub C. And again, our positive direction is down because we're dimensioning down from this datum. So what else do we know? Well, we can start by getting an equation for the total length of both these chords. So we know chord 1 has a length of, if we start at C and we go up, we have a length of SC. Then we're ignoring the length of chord over the pulley and over all the pulleys. And we're ignoring this length of chord right here, which is above the datum line, because this chord length right here will not change with respect to time. It stays whatever length it is. So from here to here we have an SC. We ignore this rope over the pulley. And then from here to here we have a length of, SE. So SC plus SE plus another length of SE is equal to the length of chord 1. And if we simplify this, we get SC plus 2SE is equal to L1. And if we get the velocity, we have VC plus 2VE is equal to 0. This L1 becomes a 0 because L1 is a constant, and when we differentiate a constant, it doesn't matter what that constant is, we're going to get 0. And if we take the derivative of this velocity equation, we get the acceleration of C plus 2 times the acceleration, 2 times the acceleration of E is equal to 0. And these are our equations for chord 1, right here, and right here. So for chord 2, we have a chord 2 here. We're going to do the same, trace the chord and find a total length. So if we start at one side, let's start right here, and we trace it up, we have a length of SW. When we go over our pulley, we ignore this, and we ignore this length of rope under this SE. So we have an SW, ignore, and this length of rope is SE. So SW plus SE is equal to L2. And VW plus VE is equal to 0, again because we're differentiating a constant, and the acceleration of W plus the acceleration of E is equal to 0. Now we have three different unknowns here. We have an acceleration of parts of this point C, we have an acceleration of W, and we have an acceleration from E. So let's use other pieces of information in this problem to try to figure out one of these accelerations. And just so happens we have some information on W. So W moves 30 feet in 5 seconds. If we write down what we know, we have an initial position of 0. We have a final position of 30 feet. We have an initial velocity of 0 because our elevator is starting from rest, which means our system is starting from rest, feet per second. And we have a final velocity of unknown. We don't know this now. We have an acceleration, which is unknown. And the time that we're looking at is 5 seconds. So if we look at all our kinematic equations that we know, we can go through them. We know a final velocity is equal to an initial velocity plus the acceleration times time. A final position is equal to an initial position plus the initial velocity times time plus 1/2 times the acceleration t squared. And a final velocity squared is equal to an initial velocity squared plus 2 times the acceleration times a final position minus an initial position. And if we compare everything we know with these equations to figure out which ones to use, we don't know a final velocity and we don't know A. So this equation and this equation both depend on the final velocity in A. So our hand is forced to use this second equation. If we plug in what we know, we have 30 is equal to 0 plus 0 times 5 plus 1/2 A times 5 squared. These two go away, and if we solve this equation for A, we get A is equal to 2.4 feet per second squared. And so this is the A of the weight. This is good for us because we know the acceleration of the weight is going to be equal to the minus acceleration of the elevator. So if we have the acceleration of the weight is equal to 2.4, the acceleration of the elevator is going to be equal to a minus 2.4. And then we can figure out the acceleration of the cable right here, because the acceleration of the cable is equal to a minus 2 times the acceleration of the elevator. And this is equal to minus 2 times minus 2.4. And this is equal to 4.8 feet per second squared. And this is minus 2.4 feet per second squared. And what does this actually tell us? This tells us that the acceleration of C is 4.8 feet per second squared, and it's positive. So C is moving down. It's moving in the positive direction at 4.8 feet per second squared. So C is moving down. The acceleration of the elevator, AE, is a minus 2.4 feet per second squared, and minus means it's moving against our positive direction. So AE is moving 2.4 feet per second squared in the upward direction because it opposes our positive convention. Now, that is part A. Part B is asking for the velocity of the elevator after 5 seconds. So if I got a different color here, part B, velocity of the elevator after 5 seconds. So we're looking for a final velocity. Final velocity. We can use this equation right here. So we have a final velocity is equal to an initial velocity, which is 0, plus the acceleration, and it's the acceleration of the elevator, which is minus 2.4. So minus 2.4 times 5. And we get minus 12 feet per second. And what does that mean? Again, that means since it's opposing our positive direction, our velocity is going this way, our final velocity is 12 feet per second in the upward direction.